Hey everyone, so welcome back. Another webinar here that discusses SIMULIAworks. My name's Omar Zoni. Again, my colleague and I, Sashi, have been working on a handful of webinars that we hope will highlight some of the capabilities available inside SIMULIAworks. Again, just to kind of give a little bit of a background, SIMULIAworks is the joint collaboration between SolidWorks, the SolidWorks brand at Dassault, and the SIMULIAworks brand at Dassault, and the Simulia brand, or the Simulia brand at Dassault, sorry. And the Simulia brand is the brand that's responsible for all of the simulation capabilities. So SimuliaWorks right now is really just kind of the Abacus tool. So it's using the Abacus solver with a really nice front end in the 3D Experience platform. And today I'm going to be talking about the Material Calibration app. So let's go ahead and get into the app and discuss exactly why, where it's useful, and the power behind it. Now, the Material Calibration app is an app that's available inside of Structural Mechanics Engineer, which is the product that gives you explicit dynamics. We'll be doing my colleague Sashi will be doing a presentation that shows some of the capabilities available with the dynamic solver. But in addition to the dynamic solver, another really nice feature that you get with Structural Mechanics Engineer is the ability to do material calibration. Now, what exactly is material calibration? Well, material calibration basically gives you the opportunity to take measured test data. So typically it's stress strain data, maybe measured in some different ways if you're doing hyperelastic materials, but you can take that test data and then fit it to one of the material models that are available inside SIMULIAworks on the platform. So, typically the material models are going to be, linear elastic, elastic plastic, hyperelastic, viscoelastic. There's also a really nice hyperfoam model. There's a viscoplastic model, but I would say for the most part, particularly customers that are coming from the SolidWorks world into SIMULIAworks are going to probably be in the elastic, plastic, hyperelastic, maybe foam, maybe viscoelastic range. Now, what are some of the challenges typically for using some of these advanced material models? Well, first of all, if the calibration tool is too difficult, you're probably not going to use it, right? So, if it's very manual, requires a lot of expertise, you're not going to use it. Now, the downside of that is that without proper calibration, the material model that you then go ahead and use is not going to fit your data very well. This material calibration app really unlocks the door to allow you to be able to really accurately model your material characteristics. Okay, so here I am in the material calibration app. Now, the first thing that I'm going to do is I'm just going to rename this to give the material name a little, to make it a little bit more meaningful, right? I'm not going to let it just be physics simulation, whatever. I'm just going to call this, so I'll just call it Webinar MC for material calibration. So what are the steps to do this? Well, the steps are pretty straightforward. First of all, we're going to import a material model, right? So I'm just going to say, go ahead and let's import a material model. Now, I have some predefined test data here. I am just going to read in the material model for a very, very simple elastic plastic an A356 material. And right here it is. So it's a simple text file that gives us our stress strain curve basically. Now, there are a couple steps that we're going to do. So this is reading the text data directly. I'm going to first say that, look, I don't want you to start the import at row 1. I want you to start it at row 2. And we can see the material test data that gets imported. So let's see. A couple things. I mean, for this guy, we really don't need to do much correction. So I'm just going to go ahead and say finish. You can see it's about 475 rows. So there's my uniaxial test data. So I'm going to go ahead and just see that my stress is in the correct unit. Now, if it weren't in the correct unit, I would have to go back and change the unit system. But it appears that we're okay. So Now, because I don't really need to make any changes to the actual curve, I can just go ahead and say, look, I want to select the appropriate material model for this. Now, in this case, I am going to use an elastic plastic material model, and um, I'm not going to have any rate dependent material properties, so I'm just going to say elastic plastic, and I'll go ahead and say OK. And then it's going to ask me, which material model do I want to use. So isotropic Johnson Cook is probably the most common for this particular model. And you can see the based on the A, B, and N materials or material constants that it's kind of just guessing at. This is the response curve. Now, obviously, that response curve is not accurate, right? So we're going to have to do some calibration in order to capture the correct response, right? So one of the things I'm going to do is I'm going to turn off. I don't want it to really iterate on the modulus of elasticity. I'm pretty confident that that's accurate. What I do want it to iterate on is the ABC constants, or I'm sorry, the ABN constants that kind of define the material property. So I am now just going to come up here to execute. I could, there is some ability to change kind of the way it does its iteration and the way it converges and what it considers a converged solution. I'm just going to leave it at the defaults. I found that leaving it at the defaults is adequate for most of the material models. So it's going to go ahead, it's going to convert. You'll see it change our A, B, and N variables as it does that. And eventually it finishes, and it's now we can see that the test data lies right on top of our response lies right on top of our test data. So a pretty simple example to capture the response. So I'm just going to close this here. We can see what our A, B, and N values are. And now if I wanted to, I could just go ahead and save this material model using the save right here. So if I go ahead and save it, now I've got access to that material model, whatever it was called, Webinar MC. So that's how you would do it for a very, very simple elastic plastic model where the curve is pretty well defined. So now let's take a look at another example. So this is an SAE 1018, a low carbon steel material model with some test data. Now there are a couple issues with the data in this case. I wanted to show you guys an example with some situations where you might have to correct the data that you get. So for this particular model, there are a couple things. First, there's a couple points that appear really close together that don't look realistic, so we're going to get rid of them. We're going to get rid of the test data after the ultimate tensile stress because there's some necking that's going to occur. We're also going to do a zero offset. There's a little bit of slack at the beginning of the characterization or the capture of this data. So we're going to account for that. So what I'm going to do is I'm just going to highlight the first two columns so that the software knows which data I would like for it to import. There you guys can see it. So I'm just going to go ahead and say finish. It's uniaxial test data. We're in megapascals, which we expect. And you can see some of the data that's real. Here's a point that's really close together, and then we're going to do a zero shift to account for some of this slack that's in the model. So we also know that for this particular model, we know our Young's modulus is going to be about 205 gigapascals. We know the Poisson's ratio is 0.33. So we've gone ahead, imported the model. If we want to, we can change the way this appears. So instead of having it be red, if I come here to my settings, you can see I can change the name of it. I can also change the color. So let's say that I want this to appear in black. And if I did want a line, I could say, hey, look, put a solid line on there, up to you. Also dashed lines, dotted lines. So you can fully customize the way you want your test data to look. All right, so I've got my test data selected. Now the first thing that I want to do is I want to do my zero shift, right? So what I'm going to do is I'm going to double click on my uniaxial data, which activates, puts me in a mode where I can actually do, make some modifications to it. So then I'm going to say, like, in this case, I'm going to zoom in. Well, let me just zoom in on anything under about 300 megapascals. I'm going to tell the software that I want to do a zero shift here, and then I'll go ahead and pick the data that I want to modify. So it's basically right around here where we've got that slack. I'm just going to grab those 4 points. I'm going to go ahead and say that I want to evaluate. All right, so that's what our new curve will look like, and I'll just say, okay. So here is my new curve, zero shifted to account for that slack. Now the other thing, you can see up here, I've got 2 points that are right on top of each other. So what I'm going to do is go ahead and remove one of those points. So I think it's right around here. Yeah, we can see the 2 points that are right on top of each other. I'm just going to highlight that one, remove that selection. I could smooth the curve a little bit if I wanted to, but not a big deal. And then I'm also going to get rid of any points above the 0.19 stress or strain. So anything above there, I'm just going to go ahead and get rid of this data because it's above the ultimate stress. And there you go. There we've got the curve that now I want to fit. So again, I'm going to say OK here. There's my data curve. And then I'm going to go ahead and select the appropriate material model here. So in this case, again, and I could name it here. So let's call it SAE 1018 MC for material calibration. I will use linear elastic. Again, I'm going to use the elastic plastic. And that should be all I need to do. So I click OK. Now it's going to show me my material model. You can see for the values that, let's make some modifications here. So first of all, we know that we don't really want to be running any calibration on the Young's modulus or the Poisson's ratio. So I'm going to turn that off, and I'm going to put in the appropriate Young's modulus. So we said it was 205 gigapascals. So, and we know that we want our Young's modulus to be around 0.3. I could play with some of this stuff, the way that it calibrates, the error measure setting that it uses, and the optimization setting. I'm going to leave them as defined. I don't think it's as important to start playing with that stuff unless you start getting some results that don't make sense. And I'm going to go ahead and say execute. And again, when I do that, it's going to iterate on the A, B, and N values. And hopefully it will give us a curve that fits the test data. All right, so there you go. Again, we can see what our A, B, and N values are. We can see the response curve really, really closely mimics the data as input. So again, I can go ahead, save that data out, and now I've got another material model that meets the criteria for the test data. Or I'm sorry, the material model that accurately corresponds to the data that we recorded. So now the last example that I want to show you guys is an example where we got hyperelastic data. Now, hyperelastic test data, this one came from a company that has allowed us to share it, a company called Axle. And the test data actually has so tension, biaxial, planar, and volumetric test data. So we've got 4 sets of test data that we want to fit to one of our hyperelastic curves. So again, first step, I'm just going to import the data. Which is right here. And we can see we've got the uniaxial, biaxial, planar, and then down here, where's our, oh, and here's our volumetric test data. So let's go ahead and start importing the appropriate curves, right? So we'll start with uniaxial. That's the first one defined up here. And I'm just going to, again, we'll just highlight the A and B columns and go ahead and import that data. And let's just to make sure that our unit system is correct. Yes, we are. We want the nominal uniaxial stress to be in megapascals. We've got our strain data defined. Um, so that seems right. I'm just going to go ahead and ask it to import the data. Perfect. So now we've got our uniaxial test data. Now I'm going to move on to biaxial. And I will select the appropriate curves, do the same thing. Biaxial test data, units are megapascals for stress, obviously the strain. So we've got our biaxial test data. Now I'm going to go ahead and define our planar. Perfect. And finally, volumetric. So I'm going to go ahead and say that I want to import the volumetric test data. And we're going to need to make sure here now that the columns are accurately defined. So column 1 will be the volume ratio, and then column 2 will be the pressure in megapascals. And yeah, that looks correct to me. So perfect. So now we'll just go ahead. We'll ask it to import that data. And we can finish. So yeah, there we've got our uniaxial, biaxial and planar, and then we've got our volumetric test data. So in this case, we've got our test data imported. Now we just need to select the appropriate material model. So in this case, we're going to use a hyperelastic. So I'm going to change the name here to hyper material calibration, and we will use the hyperelastic material formulation. Now, we don't have the unloading data, so we can't include the Mullins effect. We just have the load data. If we did have the unloading characteristics, we could include that. In this case, we don't. So yeah, we're just going to use hyperelastic without the Mullins effect. So here we've got our test data, and here we've got the assumed response based on the calibration. So obviously we haven't done any calibration. It's kind of just an initial guess. We can specify the material model that we want to use. Do we want to use, Ogden, Mooney-Rivlin? It really just depends on what material data that you have and which material. I would suggest you guys read a little bit about where these particular models work. In all honesty, if you've got this much data, there'll probably be a few that work pretty well. So what I'm going to do is I am going to use the Yao model. I will leave all of those characteristics on. I actually want it to use all of the test data. If you wanted to, you could turn some of these off and say, hey, look, I just want you to fit to the uniaxial, the biaxial, etc. Honestly, in the case where you've got all this data, I would argue that you probably want to use all of them and fit the curve that best fits all of the data that's available, right? So let's go ahead and execute and see how accurately we can mimic or follow the curve. And you can see pretty quickly we get some response data. So again, if you don't feel like this is a good approach, or maybe you can see that the biax, well, they actually are all pretty close. So, but let's just for the sake of it, let's say that we want to use a Mooney-Rivlin approximation. And then we can go ahead and execute there. And perhaps you feel like this is a better approximation of your test data. So it's kind of up to you to figure out exactly which, first of all, how accurately you want things to fit the curve data, how many iterations you want. So you can kind of control that here in the optimization. So if I wanted more iterations, if I wanted the tolerance to be a little bit tighter, I could control all of that data. But again, I mean, we can also use polynomials. If we wanted to use a high order polynomial perhaps to fit the curve, we could do that. You can see that is not really fitting our volumetric test data very well at all. So I'd argue that that's probably not a good fit. So, I mean, the bottom line here is that you've got access to a lot of different hyperelastic material models. Ogden is also a very popular one. We can use like a second or third order Ogden, which adds quite a bit of accuracy to the model. And actually, I would argue that the Ogden looks like it fits it pretty well. So maybe you want to use that one. So again, once you've got it, the appropriate model fit, you just go ahead and save the data. So there are some other more advanced material models that you can fit. I would argue that if you're getting more complicated than kind of elastic plastic or hyperelastic, maybe viscoelastic and hyper, and if you've got foam, maybe hyperfoam, that it might be an opportunity for you to reach out and work with one of the technical resources at your reseller, or reach out directly to SolidWorks. But really, really powerful tool here, the Material Calibration app, and I hope you guys, were able to see some of the power that's available inside of the SIMULIAworks. This really, really neat app on the 3D Experience platform available with SIMULIAworks. So I hope that those three examples give you a little bit of background about what is exactly capable using the SIMULIAworks tool and the material calibration app. Again, Sashi and I are doing a series of webinars. If you're interested in some more data, you can also go to the website listed here, solidworks.com/SIMULIAworks. There are a lot of videos and some resources that will allow you to figure out exactly what's behind some of these SIMULIAworks tools. In addition to that, if you have access to my SolidWorks, there's also some videos that are available there. So you can see my smiling face in one of the videos on the bottom right there. But there's a lot of capabilities there that kind of give an overview of some of the capabilities and show some examples of where they're useful. If you guys want, and here are some actual examples of the tool being used. So I believe all these are using Structural Mechanics Engineer. They all look like explicit examples. Drop test there at the top right. Can crushing. It looks like an impact test bottom left. I'm not sure what the top left is. But it does look like it's a dynamic simulation. So I think they're all probably using the explicit solver available in Structural Mechanics Engineer. If you have some questions about the webinar or anything else that I can help with, please, guys, feel free to reach out to me. Here's my email address. I'll leave it up here for a couple seconds. I know this is a weird time, and we're doing our best to try to stay engaged with you guys. But anything that we can help you with, feel free to reach out. If I don't know the answer, which is quite likely, I will refer you to the appropriate person, and we can go from there. But thanks for taking a little bit of time. Again, this is going to be a 4 or 5 part series on advanced simulation techniques or capabilities using SIMULIAworks. So stay tuned for what's next. Or if you haven't looked at the previous ones, take a look at some of the SIMULIAworks capabilities in this webinar series. So everybody take care and stay safe. And until next time, cheers.